Okay, we are on chapter 2 here, and last time we talked about something chemistry related, I imagine. I'm gonna go with like sig fig sounds maybe good. I don't know. We talked about some sig figs, I think, and again, a reminder when we count sig figs, they do come from measures, sort of values. And again, when we record a measurement, we have all the certain numbers plus that first uncertain number. And again, that is our measurement, which again has a specific number of significant figures. And that's different than something that's sort of an exact number. That's again something that is counted, something that's sort of a definition. But with significant figures, remember that all non-zeros again are going to be significant. Uh, when we talk about zeros, there's three types of zeros. We have our leading zeros, which are not significant. And those, again, are all those zeros that come before you hit the very first sort of non-zero number. They are not counted. We have sort of trapped zeros, captive zeros. Those are significant, and those are zeros, again, trapped between two non-zero numbers. And then we have the zeros at the end, which is again sometimes referred to as the trailing zero. And those may or may not be significant. And again, what determines if they are significant is if there is a decimal point written in the number that would make those zeros at the end significant. So if we had 0.00400, these zeros at the end are going to be significant because there's that little decimal point actually written, as opposed to if you say had 400 like so, nothing written, it will be just that 4 there in front would be our significant figure in that case. We also talked about sort of calculations of all the significant figures, I think. And remember, if we kind of multiply, divide, we're looking at actually significant figures. And our answer should have the same number of significant figures as whichever number in the calculation has the least number of significant figures. And that goes for both multiplying and dividing. When we add and subtract, we are looking at actually decimal places. And once again, it is the least number of decimal places is what your answer should have. The idea of what we talked about last time, I think, is again, they're both the least because that would mean that's probably your worst measurement. And again, your calculation, for example, is only as good as sort of the worst measurement you can make. Um, we also got into some prefixes and how to use those properly at the very end, I think. And remember that when we see something like centi, which is 10 to the minus 2, that really is the same as 1 times 10 to the minus 2 in sort of scientific notation. And remember that the way that you want to use this is when you see that sort of 10 to the minus 2, say 10 to the 3 for kilo or whatever it may be. That's how much there is, again, in the base unit to one of the prefix units. So a prefix unit like a centimeter would have 10 to the minus 2 of the base units, which is meters. And again, it works the same way for anybody here. 1 centigram would be 10 to the minus 2 grams of the base unit. And again, it's super common. People always kind of reverse those and kind of use it backwards. You want to make sure that you sort of use it correctly. Again, something like kilo, which is 10 to the 3, works the same way. 1 kilogram would be 10 to the plus 3 grams. 1 kilometer would also be 10 to the 3 grams. Again, the way that you put that into your calculator, if you need to, is basically just like you do scientific notation. You do the 1 times 10 to the minus 10 to the 3, again, using your exponent. We also talked about the idea that, if you're kind of going from prefix to prefix, is a really good idea to kind of take it back to the base unit because you kind of have that conversion, and then take it from the base unit back to the next prefix unit. And the way we want to kind of show our work, which I think we hit on there at the very end, and we're going to talk more about today, again, is a calculation sort of style, which is known as dimensional analysis. And that's where we take any type of equality like we had, for example, on the previous page. 1 centimeter is 10 to the minus 2 meters. That's an equality, which again are basically two values that are on different scales, but they do represent the same amount of something. So if you say you have 1 centimeter, that's the same thing basically as saying you have 1 times 10 to the minus 2 meters. It's the same amount. And from any sort of equality, we could write conversion factors, as we sort of did there in that very last sort of calculation, I think, to wrap it up last time. And these are conversion factors. And conversion factors, once again, are just fractions where basically you just put one of the values up on top as numerator, the other value on the denominator. And you have the option basically just flipping it around and putting the other guy up on top and the other one on the bottom. The nice thing about dimensional analysis, again, is it's sort of a unit cancellation, and it's a way to show your work. It also simplifies sort of the math that you have to do, and it also, in a lot of cases, can simplify the fact of maybe you don't remember the formula, but you kind of get rid of the units you don't need and get the units you do need, and it will sort of do the math for you, maybe figure out the formula for you if you just kind of take that type of approach. So again, in this situation, if we had, say, 55 meters and we wanted to know how many centimeters that would be, the way again that we kind of would set this up, as we talked about, I think in the last example, we would obviously want to find an equality that could get us there. It may be one equality, maybe multiple sort of equalities that will get you to ultimately where you want to go. We will have our conversion factors. And again, we set it up, as I mentioned, as 55 meters. And again, in this case, it's not really written as a fraction, but it's assumed that that meters are on top. And as I mentioned the other day, you know, if it helps you, you could actually just put it over one so you can visually see that the meters are up there on top. And remember, it's a really simple approach when you're doing dimensional analysis. All you essentially have to remember is opposites cancel. So whatever units you want to get rid of, you need to put the same units in a conversion factor in the opposite location. So in this case, I definitely want to get rid of meters so that I could end up in centimeters. So I do want meters in the opposite location. So meters are up on top. The opposite location here would be using this conversion factor on the left. And if I do that, I get 10 to the minus 2 meters on the bottom and 1 centimeter. Now, when we do dimensional analysis and set it up like this, it is always the same math that you're doing, which means everything on top, 100%, always gets multiplied. And whatever's on the bottom basically gets divided. And that's also a nice thing about dimensional analysis is basically just two operations. That's all you have to remember. Top multiplied, bottom divide. You know, it kind of does the math for you. So in this particular case, we're essentially going to take 55 and divide it by 1 times 10 to the minus 2. And that is going to give me, in this case, 5,500. The units of meters on top and meters on the bottom do cancel. And they cancel because essentially what you're doing is taking meters on top, meters on the bottom. You're essentially dividing those two. And basically it equals 1 and they cancel out. As I may have mentioned yesterday, kind of the same idea. If you take 2 divided by 2, they cancel each other out and equals 1. So if you have the same units on the top and bottom, they will essentially cancel themselves out when you set it up like this. The only unit that is left that will not cancel out is centimeters, which would be the units that we would end up with in this particular case. This is considered an exact number because it's a metric to metric conversion, which means you do not have to worry about it in terms of your answer. That means you do default back to the original number, which is really the only other number in here, which has two significant figures. And again, here, this answer, the way I wrote it, does have two significant figures. This is also a reason I would not want to put a decimal point at the end, right? Because then how many significant figures would I have if I put a decimal point at the end? I would end up with 4, yeah, which is too many, right? So again, this is a really way that you're supposed to show your work in chemistry. It is also, like I tell you, very beneficial because again, there's a lot of formulas that you don't even have to worry about remembering per se, or kind of thinking about how to rearrange it correctly. And, you know, when I rearrange it, should I be multiplying or dividing? If you set it up this way, 100% of the time, anything on top gets multiplied, anything on the bottom gets divided, and it just kind of takes the guessing out of it. And when you are done with the calculation, pretty much if you're just shooting for one unit at the end, that unit needs to be up on top by itself. Yeah. If you have two units, then you have a unit on top and the bottom. But that's a good way to remember. Again, you should always be sort of up on top by itself. Any questions on any of that there? Okay. So we looked at some of these conversions here. So let's take a look at these. So we have 1,000 meters is equal to 1, and that would be kilometer, right? Kilo is 1,000 or 10 to the 3. We have 10 to the minus 6 grams is equal to 1 microgram. Microgram is 10 to the minus 6 on that chart. By the way, microgram is a weird one in your book. In most places, that is actually the symbol for micro, but your book likes to use, I want to say MCG, I think, if I'm not mistaken. It's kind of weird. The only place I've ever seen it, I think, is in your book. So that is micrograms, but I feel like I've also seen that pop up in the book as well. But that is actually the micro sort of abbreviation. But I do believe in a lot of cases your book will use like MCG for that. So that's kind of a weird one. 0.1 liters is a deciliter. And again, 0.1, right, is 10 to the minus 1 in terms of what it is. And obviously, this is 10 to the minus 6 here for micro. All right, so in terms of length equalities, once again, 1 meter is 100 centimeters. We do use that a lot and see that a lot. There's 1,000 millimeters in a meter, and again, 10 millimeters in a centimeter. Once again, as we might have mentioned last time, this conversion is perfectly fine if you kind of like remembering that one or kind of using that one. It's perfectly fine. That is the same as when we look up centi, as we just talked about on the previous slide, and that's 10 to the minus 2, where 1 centimeter is equal to 10 to the minus 2 meters. If you divide both sides by 10 to the minus 2, those guys cancel, and it gives you 1 meter is 100 centimeters, sort of a bigger number version of it, and they're both perfectly legitimate and the same conversion. And the same thing with, like, for example, kilometers. Again, when we say 1 kilometer is 10 to the 3 meters, because 10 to the 3 is 1 times 10 to the 3. If you turn that into a regular number, that's 1,000 meters is 1 kilometer, right? So it's the same conversion, just sort of written in a different sort of format. Volume as well. Again, these are very common equalities. 1 liter is 1,000 milliliters. That I would say is probably the equality for volume that we use a lot, or probably the most in chemistry. And that's because of a couple of things, as I might have mentioned in a previous lecture. Most of the time when we sort of measure volume, like in the laboratory or something like that, oftentimes we do measure it in milliliters, but unfortunately, a lot of sort of calculations that you have to do, volume oftentimes needs to be put into liters. So it's a very common conversion to kind of convert milliliters to liters, and also vice versa, liters back to milliliters. So that's a very common one. Probably the other most common one that you'll come across is basically a one-to-one relationship that we talked about previously. 1 cubic centimeter, again, is 1 milliliter. So again, a cubic centimeter is basically found by kind of taking 3 length measurements and multiplying them together. If you have like a solid cube, you take a ruler out and measure like the length times the width times the height. And again, when you multiply those together, you get cubic centimeters. And again, that is the same as 1 milliliter. So those two are probably the most that we see here. And obviously our CC is another version of cubic centimeters, as we talked about. And again, obviously that's very common in, as you can see there, syringe there, and medicine. Sometimes they talk about cc's rather than milliliters and stuff like that. And again, they're all basically a one-to-one relationship between everybody. Mass equalities, I would definitely say probably these two will pop up a lot. 1 kilogram is equal to 1,000 grams. and 1 gram is equal to 1,000 milligrams. Again, these are equalities. So really, if you're going to do some type of dimensional analysis, you can write 2 conversion factors for each of those. 1 kilogram over 1,000 grams, or 1,000 grams over a kilogram, are 2 possible conversion factors that you could use in a problem if you were, again, obviously trying to go between those 2 units, grams to kilograms, or kilograms back to grams. And again, there's our microgram sort of abbreviation, I think. All right, so let's identify which unit is larger, millimeters or centimeters. Millimeters, centimeters, centimeters is larger, right? There's 10 millimeters right in a centimeter, bottom part of a ruler, typically. Kilograms, centigrams, kilo, right? Deciliters, microliters, deciliters. And again, here they use microliters, but hey, microliters are milligrams. I don't know why they just flip around the symbols there. Milligrams, yes. Then micrograms. In those cases. So again, like I said, they will kind of bounce between these kind of 2 symbols. I don't know why they just don't try to choose one or the other. But again, it's kind of the similar thing there. All right, so 1,000 meters is equal to a kilometer, right? And 0.01, which is basically 10 to the minus 2, is a centigram, yeah, or centimeter in this case, right? All right. All right. And obviously 1 kilogram is basically 1,000 grams, and 1 centiliter, or 0.01 centiliters is equal to, in terms of liters. So again, if we're not sure, we could take a look at this. We got 10 to the minus 2 for centi, right? So again, that's going to mean that in 1 centimeter, there is 10 to the minus 2 meters. So in this case, we are starting with centiliters. I guess I should use centiliters and liters here. That'd be a better conversion. And again, we're going to do a little dimensional analysis. So this is up on top. And again, to cancel, we want to go opposite. So we would go 1 centiliter on the bottom is 10 to the minus 2 liters. So in this case, we would take 0.01 and times it by 1 times 10 to the minus 2. And that's going to get us 0.0001 liters in this case. Once again, the centiliters on top and bottom will cancel. Once again, we're multiplying the top and dividing the bottom. So it looks like it should be that one, even though I feel like they're going to choose the wrong one. Oh, they did choose the right one. That's good. Any questions on those there? Okay. So we've just sort of touched upon it, but let's officially talk again about writing conversion factors. And again, it's really a critical part of doing dimensional analysis or problem solving. And as I mentioned before, from any type of equality, we can write 2 conversion factors. And again, as we've been talking about, again, an equality are 2 things that represent the same amount, but are in different units. They can be between the metric system, they can be between the US or English sort of system, and you can cross over metric to US. So as we'll talk about, in certain cases, if you are using an equality and thus a conversion factor that came from that equality, there are certain times where you do need to sort of take into account when you're doing a problem, the significant figures in that conversion factor. There are other times where you don't need to take it into account, and the 2 main times when you don't really need to take it into account is if you're using some type of conversion factor that came from an equality that is a metric to metric equality, or a US to US sort of equality. Typically speaking, as we will see, as you cross over from sort of metric to US units, and you're using a conversion factor from that, that is not considered sort of an exact number. So this is metric to metric. And again, we could have 2 conversion factors for this guy that we could use in a problem. And again, it's just simply a fraction where you put one on the top and the other on the bottom, and then you flip it. We also could go a pound over 16 ounces, or 16 ounces over a pound. And here we could go 2.20 pounds over a kilogram, or 1 kilogram is 2.20 pounds. So these again are all the conversion factors that you could write for each of these equalities. This is a metric to metric equality. This is a English to English or US to US equality. And this is actually a US to metric sort of equality. Now, out of all three of those, this would be considered an exact number, which means when we use it in a calculation, we don't have to worry about the significant figures in it for our answer. This would be considered an exact number. This you would actually have to look at it again because it's a crossover between metric and English in terms of conversions. And when you do look at, for example, this conversion factor and you had to count the significant figures in this case, you would look at the actual one that's a number, not the one that's actually the number one. Yeah, so you would look at the 2.20 there, and you would count it as three significant figures. And then you would look obviously at your other numbers you need to look at in your calculation and then make your decision as to, how many significant figures your answer should have. Obviously, we see sort of the different units as we talked about a lot of times on groceries, right? They kind of give it a lot of times in grams or kind of a US sort of unit like ounces. Um, Equalities and significant figures, as I just mentioned, they are considered exact if they're kind of, again, metric, English. But again, once you kind of cross over, you do have to sort of take those into account. So all of these here on this screen would be considered exact numbers. And if you use any of them in a calculation, you wouldn't have to worry about the significant figures associated with it. All these here are crossing over from basically metric to US. And because of that, we would have to sort of look at the significant figures here. So 1 pound is US and 454 grams is metric. So again, here, this guy would count as three significant figures. This also is milliliters to quarts, which is a crossover. That would also count as three significant figures, and inches and meters obviously would also count as three significant figures. So that is really the only time when you use a conversion factor that you have to worry about the significant figures in it is if you kind of cross over. Other than that, you can almost, autopilot it. It's like you don't have to worry about those in your calculation. There is one sort of exception that is considered an exact number that is sort of a crossover between metric and English, and that is this one here. 1 inch is exactly 2.54 centimeters. So this is considered, even though it is metric to English, an exact number. So if you happen to be using that conversion, you would not need to worry about it in terms of your calculation. Remember that most of the time you're going to be using your conversions, doing dimensional analysis, which means mathematically what you're going to be doing pretty much all the time in dimensional analysis is multiplying and dividing, which means when it comes to your answer, you are looking at for the least number of significant figures in your calculation, right? So it's always going to be significant figures. Another benefit of sort of dimensional analysis is it's only multiplying and dividing, which means when it comes to your answer, you always know what you should look at is always significant figures because that's all you're doing in that type of calculation. Conversion factors, as we've been talked about, again, just simply fractions. You can put one over the other. 1 hour equals 60 minutes. Again, that is an equality. That gives us two, obviously, conversion factors we'd use. With any conversion factor like this that comes from an equality, you will never use them both in the same calculation because you will undo your calculation. You will just use the one that you need. So for example, here, clearly, if I had 30 minutes and I want to know how many hours that would be, again, we would set it up by going 30 minutes. And again, if it helps you out, throw that one underneath it so you can visually see that minutes are on top. And we know we want to get rid of minutes. So once again, that makes our choice of conversion factor fairly straightforward. Opposite location for minutes, which is on the bottom. And we would obviously set it up like so. And again, as we've been talking about, up on top, we multiply, on the bottom, we divide. So we're essentially taking 30 divided by 60, gonna give us, on our calculator, by the way, it gives us this number here, 0.5. The minutes will cancel. That will leave us hours at this point. Now we want to think about significant figures. And in this particular case, this is an exact number because it is a conversion there that's exact. That means we do come back to this. And actually, the way I wrote that 30 is how many significant figures? It is actually just one, which I guess I got it right here on my calculator this time. How's that? That should be 0.5 hours would be the proper answer based on that question. So when you're doing this, you just want to kind of keep it simple. Three things to remember, basically. Opposites cancel, multiply the top, divide the bottom, basically. Yeah. Here are some common equalities. And again, they will be pretty much provided for you. Again, you just need to be able to obviously use them correctly. Some things may not be provided for you, like maybe some things you hopefully should know, right? So there are how many seconds in a minute? And how many minutes in an hour? And hours in a day? Yeah, so it's 24, not 60, which is again the same last. So something like that may not be provided for you, but we will probably, if we look at the metric here, you will come across, pretty much a lot of the ones on this sort of list here. These are all equalities. These are all equalities that for every single one, you can write two conversion factors like we've been talking about. Once again, everybody in this column would be considered an exact number, again, because it's basically a metric to metric conversion, which means you do not need to worry about significant figures in your calculation. These are all US ones, which a lot of them do pop up a lot. Obviously, inches, feet, and miles pop up a lot. Quartz and that type of stuff does. And definitely time pops up. These would also be considered exact numbers. Again, they're kind of US to US conversions, which means if you use any of those, you really, again, don't need to worry about the significant figures that are there. Again, it's really when you get to this column, you should look at the sig figs, except for this one, which obviously, as we just talked about, is considered an exact conversion. But once again, pretty much rolling through all these, you would look at the significant figures there if they were in the calculation you were doing. And once again, in most of those cases, if there is like a one of something equals a number, the number is the one you look at. You could have, one like this where you have a couple of numbers on both sides. So you do need to look at both numbers on both sides. But most of the time, it's just the one that's an actual number and not the one's not a number, but those you do need to look at. All right, so again here, writing our conversion factors, 1 meter equals 100 centimeters, 100 centimeters on top, 1 meter on the bottom, and obviously we're flipping it there. And our 2.2 pounds is equal to 1 kilogram. So let's just say, for example, let's say you had 6.55 pounds of food in a man versus food eating challenge, right? And you needed to know how many grams that was. Why don't we go to grams? Why not? Let's try it. Why don't you give it a try? So use some dimensional analysis, use some conversion factors. You got your pounds. Okay, so let's take a look. So clearly we want to think about a pathway to sort of get us there. So we got pounds here. We have a nice little equality conversion factors here. So clearly we could go from pounds to kilograms, and then we could take the pathway of obviously kilograms to grams. We have our one equality there on the bottom. We can obviously figure out our other equality from our kilo. So again, that is in 1 kilogram. 10 to the 3 grams. So again, that would be the equality that we can get from kilo. That is also going to give us two possible conversion factors, 1 kilogram over 10 to the 3 grams, or we could flip it around, 10 to the 3 grams over 1 kilogram. All right, so we're ready to kind of start our calculation here. Where I want to do it is the question. Maybe I'll do it up on top. So we're going to start with the number that was given to us here. So we can go 6.55 pounds. Once again, not really written as a fraction, but again, just to visually maybe see where everything is. You can put it over 1 if you like. And that again tells us that our pounds are on top. So again, by doing that, it should make your decision making when you come to our first set of conversion factors pretty straightforward. Again, opposites cancel. So should I use the one on the left or the one on the right? To use the one on the right, right? So this is the one where pounds and there's an opposite location. So we'll use that to do it. We're going to go 2.20 pounds is a kilogram. Now, it is up to you. If you want to get an answer at this point, you can. You don't have to. If you do get an answer at this point, once again, I would not round a lot because you are going to then take that number and continue on with the calculation. You don't have to stop at this point. What we do know, hopefully, is if I stop right at this point, once again, dividing the bottom, right? So we're basically multiplying and dividing. The units, the pounds on top and bottom, which are in opposite locations, will cancel each other out. That means if I lay up my calculation right here, I'm in units of what? I'm in units of kilograms. And because I set it up like this, there is no doubt that my kilograms are on top or bottom. They are on the top, right? So again, we do not want to keep kilograms. We want to get rid of them. So once again, it makes our decision pretty straightforward. Since kilograms are on top and I need to get rid of them, I need to put kilograms now on the bottom, right? Opposite location. That means right there should be the correct conversion factor. And you can continue on with the calculation here and pop that in the right. Themselves out. And now the absolute only unit that is left is grams. It's up on top by itself, which is good because that's where it needs to be if that's where I'm going to end up with. At this point, I did set it up here dimensional analysis way, and now I clearly should know, mathematically speaking, everything that's on top gets multiplied, right? And everything on the bottom gets divided. And that's all I have to remember in terms of the math part of this. So I'm going to grab my calculator. I'm going to take 6.55. We're going to multiply it by 1 times 10 to the 3, which is the 10 to the 3 at the end there. By the way, when I'm done doing that, I'm going to hit equals on my calculator. I'm then going to divide it by what's on the bottom. And the only real number that's on the bottom is 2.2, basically. Everybody else is 1. We're going to divide it by 2.2. And I am going to end up with, I'll come right about here, 9, 7.217. And in terms of significant figures, this conversion factor here that we used at the end, this is an exact number, so we don't have to worry about it. The first one that we use between pounds and kilograms is a number conversion that we do need to look at. And again, we would look at this number here, which would look at our original number, which happens to be 3 significant figures. And again, because we are only doing multiplying and dividing, I do look at sig fig versus figures is actually 3. There, I do need to look at the number next to it and round up. And I should come up to 2980. It's the only unit left. Put well there. Should not, because there will be 4 significant figures. Should I only write 298? No, that's 3 significant figures, but the meaning is much different than what it should be, right? So again, you don't want to do any extreme rounding like we talked about, that you change the meaning of the number. Any questions on that calculation there? Say it one more time. The first number of times. You could have. Yeah, you could have in that case. And again, that brings up a really good point. You should get if you do that there, you actually should get pretty close to the same answer. You should be. You might get slightly off because the true value there is like 453.6, but it's perfectly fine. And that brings up a really good point. When you're doing conversion problems like this, there are multiple sort of pathways you could go to get there. I just happen to take this pathway because we were going to use the one on the bottom. But there are definitely multiple ones, and they should all get you to the same end result. It should be super fairly close if everything's like a real legitimate conversion that you didn't make up. But that's perfectly fine. That's correct. There is actually, as you mentioned, a direct conversion. Obviously, as we saw earlier, that you go directly from pounds to grams. It's perfectly fine. Yeah. Other questions? All right, so let's take a look at some of these equalities that we saw there. So again, 1 liter is 1,000 milliliters. And again, that's going to give us our two conversions. Inches to meters, so 39.4 inches is 1 meter. And again, that's going to give us two sort of usable conversion factors. And again, our microgram there, 1 milligram is equal to 1,000 micrograms. And again, you have 1,000 micrograms over a milligram or a milligram over 1,000 micrograms. Yeah. So yeah, as was the question, there are multiple ways to get there. And in most cases, I would say that if you're just kind of doing a conversion using some type of equalities, I would say there's usually either a 1, 2, or 3 sort of step will probably usually get through there. If you're doing like a ton of steps to try to get you to some type of conversion, you might well be going on the wrong sort of path. So usually it shouldn't take too many sort of conversions to kind of get you to where you want to be in most cases. So if you find yourself doing like 6 or 7 conversions in a row, probably, maybe you're going around too much and stuff. Now, as we've been talking about, where you do have to take into account that sort of metric to English conversion, a lot of times in problems, you are sort of given a conversion factor within the actual problem itself. So for example, if you had in a problem that your car is traveling 85 obviously our metric system here, 85 kilometers per hour. That is a conversion factor that you can use. Whenever you have something that says, for example, like kilometers per hour, miles per hour, that's basically a fraction. And typically the number will say with the first unit and the second unit is 1. So here, obviously, this can be turned into our two conversion factors. And in this particular situation, because this kind of conversion factor is specific for the problem, clearly not every car travels at that rate. We would have to take into account the 85 in this case in terms of significant figures. So there's really kind of two situations where you probably would have to take into account a conversion factor, one being a metric to English conversion, or another one would be a situation like this where the actual problem gives you kind of like a specific conversion that's specific to that problem. Example, if you had a tablet that contained 500 milligrams of vitamin C, we could also turn that into a usable conversion factor. That means, again, in one tablet, you would have 500 milligrams of vitamin C or 500 milligrams of vitamin C is in one tablet. In this particular case, we would, again, because this is specific for this problem, we would have to look at that measured value of 500 the way it's written. And in this particular case, because there's no decimal point, it would carry one significant figure when we're kind of doing our calculations. And that probably, I would imagine, would be the one that would determine how many places you should go to for your answer. Another really common thing that we do and turn into conversion factors is percentages. And percentages is oftentimes something that if you're going to do a calculation with a percentage, a lot of times a dimensional analysis approach and sort of a conversion factor approach is really the best approach to do. Now, when you have a percentage, the easiest way to kind of turn it into a usable sort of number is to assume like you have 100 of something, right? And it's kind of like the same idea. For example, if you got a 90 on your exam, you probably got 90 points out of 100, basically, right? It was 90%. So, for example, if we have 18% body fat by mass, that would mean, for example, you have 18 kilograms of body fat per 100 kilograms of body mass, or you could flip it around as well. In this particular case here, we would look at the 18 as the number of significant figures that we would want to count in this case, which would be 2. This would be more of a metric approach. You could also do the same thing in an English to English sort of conversion, pounds to pounds. It would work the same way. It'd basically be 18 pounds of body fat per 100 pounds of body mass, right? So you could kind of do that with any type of percentage as well. Again, a doses as well sometimes is given in problems. So if you have some Keflex and it's 250 milligrams per capsule, again, that means you got 250 milligrams per one, basically, capsule of that medicine, and vice versa there. Here again, the 250 is a measured value and would have to be taken into consideration when we do our calculation. And again, in this case, the way this one is written, it would count as 2. All right, so write the equality and 2 conversion factors for each of these. So why don't you give it a go and see what you come up with. Is 10 to the minus 1. So again, that would mean in 1 decimeter, there would be 10 to the minus 1 meters, which would give you a couple of different conversion factors. Obviously, something like so, or just flip it around. Now, the second one here, we have 18% gold. There's a few different ones you could choose, depending if you want to kind of do grams of grams or kilograms of kilograms. You can do pounds of pounds, really. But for example, you could do something like there's 18 grams of gold and 100 grams of the jewelry. And again, that would give you your 2 conversions. Again, you could also do something like kilograms of kilograms or pounds of pounds, like I said. 1 gallon of gas equals 240. Yeah, where did I go find that? So that was probably expensive when they wrote the book, maybe. So that basically means 1 gallon of gas will cost you $2.40. And that would give you, obviously, your 2 conversion factors are your 240 over 1 gallon in this case. Any questions on those there? There you go. And they did actually go with grams on that one. This is the middle one. So again, I would say, for example, the bottom 2 there, B and C, if you had that in a problem, you should look at those conversion factors for significant figures in your calculation. In the case of the middle one, once again, you would look at the 18, and the bottom one, you would look at the 2.40, which would be 3 significant figures in terms of significant figures for your calculation. The top one you would not look at, as it is basically metric to metric conversion, consider an exact number. By the way, that once again is what we see here is the same as what I wrote on the previous page of 10 to the minus 2 meters equals 1 decimeter. If you divide both sides by 1 times 10 to the minus 2, those cancel. Gives you 1 meter is equal to 10 decimeters. So that's where that conversion comes from. So again, that's similar to the 100 centimeters equals a meter, and the same as thing as 10 to the minus 2. All right, so we've kind of been putting this stuff together, but officially, problem solving is more commonly referred to as dimensional analysis. And as we've been talking about, again, this is really the way that you should be showing your work here in chemistry. And it has a lot of benefits, as I've been talking about, in terms of, maybe helping you with the math part, not having to rearrange certain formulas. There are several steps that you want to kind of do when you approach a problem solving type thing or dimensional analysis sort of question. You obviously want to identify what is given to you in the problem. You should also think about what you're trying to find. And you really want to think about sort of a pathway that will get you there. And as we've been talking about as well, there can be multiple pathways depending on sort of what conversions you sort of choose to go with. Once you have that, you want to think about the equalities that's going to get you there, the appropriate conversion factors that go with it. And then obviously you want to kind of set up your problem like we've been doing on these examples where we see the units on top and bottom canceling out as well. So for example, here we have 178 pounds, and we want to know what is the body mass in kilograms. So let's just say, for example, the equalities that we know are maybe just these. They're the only ones that maybe we find that there are 454 grams in a pound, and like the kilo is 10 to the 3. So why don't you give it a go? Again, this is sort of the qualities that I found. Again, there are definitely other ones that you can. The way here is I got pounds and I eventually kind of want to get to kilograms. So my route is I'm going to stop over to grams first and then kind of go in that direction. Since maybe that's the first equalities I found on the sheet. So in this case, we want kilo to go with kilograms and grams, right, as sort of our equality. Once again, 1 kilogram in this case would equal 10 to the 3 grams. So once again, that's our equality. We could do our conversion factors here. We would have 454 grams over a pound. Our 1 pound is 454 grams. For our equality here, we could have 1 kilogram over 10 to the 3 grams, or 10 to the 3 grams over a kilogram. We're going to start with the number that was given to us there, 178 pounds. Again, you don't need to put the 1 there, but if it helps you just visualize where the units are, go for it. Now, again, this just makes it super easy, I hope. I know I got to get rid of pounds, and pounds are on the top. So when I go to my pounds to grams conversion factors, there should be only one choice that sticks out to you. That has pounds again in the opposite location. And that is what I'm going to use first. So we'll go for, I'll write it right, perhaps 454 grams on top and put some pounds there on the bottom, I think. And 1 pound on the bottom. Once again, we're going to multiply what's on top. We're going to divide by what's on the bottom. Pounds on top and bottom will divide out. If I stop right at this moment, I'm in units of grams, right? Which is close to what I want, but I do want to go to kilograms. And again, by writing it like this, I should clearly see that grams are on top. So to get rid of grams, I should use the conversion factor there on the left or right. I should use the one on the left. That's going to put grams in the opposite location. And once again, you could get an answer at this point. And if you do, I would not round too much and just kind of continue on. Again, I'm going to go 10 to the 3 grams, 1 kilogram. Grams on top and bottom will divide out. I am still multiplying on top and dividing on the bottom here. That is it, because I have now hit kilograms, right? Which is where I want to stop. Once again, that is a 1 unit ending point. That 1 unit is by itself up on top, and that's where it needs to be if you want to do it correctly. Here we're going to multiply basically 178 times the 454. Once again, that's all the numbers I need to multiply up on top. We want to hit equals. We're going to divide by what's on the bottom, and really everything on the bottom is a 1 except for the very last number, which is basically 1 times 10 to the 3. And again, you want to put that into your calculator correctly. So 1 exponent 3, and you should end up with, on your calculator, 80.812 kilograms. Now we want to look at perhaps some significant figures. This one is an exact, we don't need to worry about. This one we actually do, the way it's written, and that is actually 3 significant figures from the top number. The original number we always probably should look at, and that's going to be 3. That means we really should end up at 3 significant figures here, which would be 80.8 kilograms. Yeah. First off, any questions on that calculation? Now, you may be saying to yourself, didn't we just kind of do that conversion a second ago and we could have like shortcutted it? And we could have, right? If I would have saw All right, what do you remember the equality we just looked at, which was like 2.20 pounds is 1 kilogram. We could have hit there in one step, right? Which again will give us the same answer. So if I did that just like we used a second ago, 2.2 pounds is 1 kilogram. Our 1 kilogram is 2.2 pounds. We would start with our 178. In this case, pounds need to go on the bottom. So we're going to go this way. 1 kilogram, 2.2 pounds. Pounds on top are going to cancel as we multiply and then divide on the bottom. So we take our 178 divided by 2.2, gets us on our calculator 80.909090. And again, kilograms. In this case, we do need to look at this. This would be 3 significant figures. That would be 3 significant figures, takes us to there, hits us an 80.9 kilograms, pretty much the same answer, right? And it's always slightly different because we rounded on that 454 rather than the real number. So both ways are perfectly fine. It just kind of depends, what sort of pathway you kind of choose. Sometimes there's a more direct way to get there, and it doesn't matter if maybe it takes you a couple extra conversions. Again, if they're all legitimate conversions, you cancel out everything correctly. They all should get you to the same sort of spot at the end. Any questions on that there? Yeah. Yeah, so for example, I imagine on the test, most people probably use the conversion, the equalities I put on there, and would be my guess. But, if you use another one, and by the way, it's a legitimate conversion, not like one you made up in your head, but if it's a legitimate conversion and if the answer I got was 80.8 and you got 80.9, you're probably okay. And I would say in pretty much all cases. I'm pretty good at catching. It's like just slightly rounding and stuff like that. Again, as long as you didn't do any weird extreme rounding where, you end up because of your extreme rounding, instead of like 80.8, you end up like at 77 or something like that, pretty far off. All right, so let us roll. And I think that's what they use there. So perfect. All right, so let's do this one. A rattlesnake is 2.44 meters long. How many centimeters is a snake? And as we know, centi, right, is 10 to the minus 2. So why don't you give it a go? Let's see what you come up with. Okay, so once again here, we're going to relate centi. Obviously, we got meters. We're going to go centimeters. This is going to be a direct conversion. So 1 centimeter is going to be a 10 to the minus 2 meters. That again is going to give us our two conversion factors that we can use. And again, a reminder that when we see this is the same as 1 times 10 to the minus 2 in scientific notation. So we're going to go 2.44 meters. Again, meters are up on top, so we definitely want to go opposite here. So we're going to go opposite. And 10 to the minus 2 meters. Again, we're going to multiply the top, divide the bottom. The meters will cancel. And we're going to, again, if you're going to punch this in 2.44, we're going to divide 1 exponent button, negative button, and 2. Yeah, that's the proper way to punch that in. And that's going to get us 2.44 divided by 10 to the minus 2. And that's going to give us 244 centimeters in this case. Once again, this is going to be an exact. We don't need to worry about it. Here we have 3 significant figures. So once again, our answer should have 3 significant figures as well. Any questions on that there? So again, however you need to punch it in terms of exponent, make sure you're using your exponent button. But again, a reminder that when you do see this 10 to the minus 2, that's really the times 10 part we're kind of seeing there. Those are basically the same thing as in scientific notation, yeah. And basically it means, as I mentioned, it's a 1 in front now. All right. Go. Obviously, as we've done in some examples, you can use multiple ones at a time. It is really your option. I don't care if you want to get an answer up to the first conversion, then use that number to do the next one. As I mentioned earlier, if you are going to do that, just make sure you don't round too much until kind of the end. Or you could just keep going and, as many conversions as you sort of need to. Just keep everything top and bottom is really important. Uh, so a doctor orders a prescribed doses of 0.15 milligrams. If you have it in 50 microgram tablet, how many tablets would you need? So again, in this particular case, we actually have a kind of conversion given to us, which is this part. We basically have 50 micrograms, right? I guess micrograms per tablet. Or in a tablet, right? There is 50 micrograms, right? Now we want to give a dosage of 0.150 milligrams. We do have a little situation here, right? We cannot use our conversion factors because the grams there are in different prefixes, right? Mine's in milligrams, and the kind of conversion factor there is in micrograms. So you have an option as either convert your conversion factor to milligrams, or obviously before you begin, you would need to convert your milligrams into micrograms. So that's probably the move that you might want to do. So we have here 0.15 milligrams, and then we also have our 50 micrograms per tablet. Our a tablet is 50 micrograms. So why don't you give it a go, see what you got, but you do need to get this unit and like this unit together. So to give you micro is 10 to the minus 6. So why don't you give it a go? Milli obviously is here 10 to the minus 3. Yeah. All right, so why don't you give it a go? All right, so let's take a look. So obviously in this case, as we mentioned, in order to really kind of use our conversion factors, which was given to us sort of in the problem, we do need to kind of get this guy into the same unit so everything cancels out correctly. So we want to get into micro and millis. So once again, in this case, in 1 milligram, there would be 10 to the minus 3 grams, which gives us again an option of these two conversion factors to use. We also will need to go to micros. So in 1 microgram, there are 10 to the minus 6 grams, which gives us these two conversion factors to use. All right, so we can now kind of convert our 0.150 milligrams into micrograms. So again, taking that dimensional analysis approach, once again, milligrams are up on top. So opposite to cancel. So that is going to make my choice hopefully pretty easy. I need to put milligrams on the bottom here. So we'll go milligrams on the bottom. 1 times 10 to the minus 3 grams up on top. That's again going to be multiplied and divided. When it is divided, the milligrams will cancel. Once again, at this point, what we're really doing, as we talked about last time, is going from a prefix to prefix sort of conversion. So again, we're going to take it back to the base unit, and from the base unit to the next prefix. That way you don't mess up, hopefully. At this point, grams are on top. So once again, we want to get rid of grams. So we got to put grams in the opposite location, which means when we go to our next one, we need that conversion factor to do that. And that's 10 to the minus 6 grams is 1 microgram. Once again, we're still multiplying and then dividing on the bottom. In this case here, we're going to take 0.150 times 10 to the minus 3. Once again, just so we're clear, that is 0.150 times 1 exponent -3. So again, 1 times 10 to the minus 3 is what that represents. I'm going to hit equals. I'm going to come back and divide what's on the bottom. And really, the only number on the bottom there is 1 times 10 to the minus 6, basically. So we're going to divide it by 1 times 10 to the minus 6 if I actually put the right number in there. And again, this is basically 1 times 10 to the minus 6. And if I do that, I got me 150 micrograms. Yeah. So that is basically the doses we want to give this person in micrograms. And that's going to work really well since our tablets are in micrograms per tablet. Now we can really just kind of use our conversion factors to figure out how many tablets we need to give this person. And it's still the same dimensional analysis. So once again, if it helps you, go for it. Just put a 1 on the bottom, and now micrograms are on top. And that makes, once again, hopefully our decision pretty straightforward. We're going to go with micrograms on the bottom here, and that is the one that we want to use. And if we do that, 50 micrograms is 1 tablet. We're still doing the same dimensional analysis, multiplying and dividing. So hopefully you kind of see that it's the same sort of math, right? Multiply, divide, opposites cancel, just keep rolling with it, right? So we're going to divide basically the 150 by 50. And that is going to give us 3 tablets here, I think. Now, if we're going strict significant figures, technically speaking, that's an exact, and that really has 3 significant figures, which means technically this has 3 significant figures, and this guy technically has 2 significant figures. So 3.0 tablets if we're going strict significant figures here. In this case, maybe the book might just go with 3, figuring you might not want to break a pill in half, maybe to give somebody it, right? So probably a whole number. But if we're going straight sig fig wise, we really should end up with 3.0 in terms of sig figs. Any questions on that calculation there? So again, sometimes you may have a conversion factor that you need to use, but the number you need to use it with is not in the right units, right? They don't match. So you got to always make sure if you're doing dimensional analysis, which ultimately is just canceling out units you don't want, you got to make sure that they're all in the same units so that they do cancel. Otherwise, they won't cancel correctly if you don't get them to the same units. Any questions on that there? All right. Yeah, I see. I figured they would go just straight up 3 tablets. So that's good. All right. We'll skip that one, maybe. Hopefully, yeah. I was to this one here. We are on a treadmill at 65 meters per minute. How many minutes will it take? We want to know how many minutes. Minutes is a time. That's obviously a distance or length. But what we have that's going to allow us to kind of get from a distance or length into time is this, which is a rate. It has both of those things in there. It has a distance or length. It also has a time component. So that's really going to be our conversion factor that allows us really to go from like length into time, which is ultimately where we want to end up. So that is basically conversion factor we can use, 65 meters per minute. Or in a minute, you could go 65 meters. We know we are going 7.5 kilometers. And again, we're looking for basically how many minutes to do that. Again, here we cannot use our conversion factors and our first number there together because the distance or length unit is in different units, right? We have kilometers here and meters here. So we do need to get them into the same unit. So I'm going to convert kilometers into meters. Once again, here, that would mean 1 kilometer is 10 to the 3 meters, which will give us 1 kilometer over 10 to the 3 meters, or 10 to the 3 meters over 1 kilometer. So starting with my 7.5 kilometers, again, kilometers are up on top, so we're going to go opposites to cancel. That will give us 10 to the 3 meters, which once again is 1 times 10 to the 3. and that's going to give us 1 kilometer on the bottom. That's going to multiply and divide here. Kilometers are going to cancel. Ultimately, here we're taking 7.5 times 1 times 10 to the minus, or 10 to the 3. I keep wanting to put a minus on that. 7.5 times 10 to the positive 3. Going to give us 7,500 meters. Now that I have it in meters, my conversion factors here are now good to go. Again, still going to take a dimensional analysis approach. So my meters are on top. I know I want to get rid of them. So again, going to go with the one there on the right, which puts it in the opposite location. And that's going to get us here 65 meters in 1 minute, basically. Meters are going to cancel. Again, multiplying the top, dividing the bottom. So 7,500 divided by 65, gonna get me here a 115.3846154 on my calculator. These obviously would be minutes. Now we need to think about sort of significant figures, obviously. So on our first conversion here, that's an exact number, so we don't have to worry about it. This one has 2 significant figures, which means when I drop down here, this should also have 2 significant figures. Again, our conversion factor we do need to look at, and that is the only number that we really need to look at, which also has 2 significant figures. So it does look like 2 is a winner here. 2 significant figures is going to take us to the second one. We want to look at the 5 next to it and round up. So that is 120 minutes on the significant figure round there, yeah. Question on that calculation there. All right. So again, it's important to make sure things are in the right units, and hopefully you're starting to get the idea that if you set it up like this, it does kind of make your options pretty straightforward. Just remembering, again, opposites are going to cancel. Any questions on that one there? Okay. All right. Let's try one last one here to wrap it up. All right. So let's say we went to the local AM PM and you went to the Thirst Oasis, got yourself some cubed ice, crushed ice. Who goes cubed? Everybody goes crushed. And you got yourself a 32 fluid ounce Diet Coke. How many gallons of Diet Coke did you drink? Here's some qualities and conversion factors that might be helpful. So give it a go, see what you come up with here. Okay, so since we're getting to the end, let's take a look. So we're starting with fluid ounces. We ultimately want to get to gallons. Again, based on what I chose here, we're going to kind of go quart in between. That's going to kind of tie those two together. So we're going to start with our 32 fluid ounces. Once again, if it helps you, put the 1 underneath it. That shows us our fluid ounces is on top, and we know we need to get rid of it. So when I look at my 2 options for conversion factors to go from fluid ounces to quarts, it makes sense that I'm going to go with this one here, which puts it in the opposite location. We're going to go 32 fluid ounces, 1 quart. Just like we always do, we're going to multiply the top, divide the bottom. That's going to get rid of our fluid ounces. If I stop right at this point, I'm in units of quarts, which is close to what I need, but I do need to get to gallons. So again, quarts are on top. So to get rid of it, once again, going to our second set of conversion factors should make it straightforward there. Again, quarts are going to go on the bottom there to cancel. We're going to go 4 quarts and 1 gallon. Again, still multiplying on top and still dividing on the bottom. Quarts are going to cancel. Going to leave us gallon as left over. So basically 32 up on top, divided by 32, hit equals, divided by 4, going to get us here 0.25 gallons of Diet Coke. Again, we really don't need to worry about that as that's an exact. Here, we also don't really need to worry. So really 2 significant figures is where we should be. The answer, by the way, is not 1/4 because it makes me just think you're too lazy to divide it. Yeah, so don't ever leave an answer in a fraction. Always divide it out and get one number with the proper units. Any questions on that there? All right, we'll wrap it up there for today.